Here's our first problem. The limit as x approaches 3 of x squared minus 9 over x plus 3. Remember the first thing we want to try? We want to try plugging it in. So I'm going to plug 3 everywhere I see an x. Three squared minus 9 over 3 plus 3. So that's 9 minus 9 over 6. And that's 0 on top because 9 minus 9 is 0. And 0 divided by 6 is 0. So the limit as x approaches 3 of this equals 0. Did you do a happy dance? There wasn't a 0 in the denominator. Example number 2. The limit as x approaches negative 3 of x squared minus x minus 12 over x squared plus 3x. The first thing we always want to try is plugging in negative 3 to see if we get that denominator equal 0. Remember that sad face that I had in the intro? So let's plug negative 3 in here. So I have the quantity negative 3 squared plus 3 times negative 3. Negative 3 times negative 3 is 9, and 3 times negative 3 is negative 9. And 9 minus 9 is 0. And we don't like that. We don't want 0 in the denominator because we can't divide by 0. So we need to think to ourselves, can we rewrite this? What strategies do we have? Let's try to factor. The top can be factored to x plus 3 times the quantity x minus 4. And the bottom can be factored to x times the quantity x plus 3. By factoring, I'm able to make a 1. X plus 3 divided by x plus 3 is 1. And I can do this because the top is multiplied and the bottom is multiplied. So on the top, I have x minus 4 over x. And now I just need to plug negative 3 in. So I plug negative 3 in the top and the bottom. Negative 3 minus 4 over negative 3, and that's negative 7 over negative 3, and a negative divided by a negative is positive 7/3. So that's the answer to this one, and I got this by factoring and making a 1. Question number 3. The limit as x approaches 2 of 1 over x minus a half over x minus 2. Let's try plugging 2 in. When I plug 2 into the denominator, I get 2 minus 2. Which is 0. What we have here is a complex fraction. I have a fraction over a fraction, and that makes things difficult. So what I'm going to do is I'm going to multiply what I like to call a fancy number 1. I'm going to multiply the numerator by 2x and the denominator by 2x. And I can do this because 2x over 2x is 1, and multiplying anything by 1 doesn't change the quantity. Why am I multiplying by 2x? Well, that's the least common denominator of x and 2, and so that's why I chose 2x. So let's simplify this. Okay, 2x times 1 over x is the same thing as 2x over x. 1/2 times 2x with this negative out in front is 2x over 2. And on the bottom, I have x minus 2, 2x. If I simplify the top, this makes a 1, and this makes a 1. And that's the whole reason why I chose that 2x. So I have 2 minus x over the quantity x minus 2 times 2x. Now, if you remember the last problem, it was really nice because I could just make a 1, but I can't make a 1 right now because this says 2 minus x and this says x minus 2. So I want to get these to look the same, and I'm going to do that by factoring. I'm going to factor out a negative 1 right here, and then you'll see the magic happen. I'm going to divide out a negative 1. So 2 divided by negative 1 is negative 2. And then this negative x divided by negative 1 is positive x. And I'm just going to rewrite my bottom. And now this is the same thing. I mean, if you want, you can rewrite this to x minus 2, that's the same thing. X minus 2 divided by x minus 2 is 1. So now I have the limit as x approaches 2 of negative 1 over 2x. And now I can just plug that 2 in. So I have the negative 1 over 2 times 2, which is negative 1/4. Question number 4. Doesn't this one look fun with this square root? Again, one of the ways we can tackle this problem is by multiplying by one of those fancy number ones. What I'm going to do is I'm going to multiply by the conjugate. What's the conjugate? Well, the conjugate of this, and I'm going to put a multiplication sign, is the square root of x plus 5. Now, I can't just multiply by the square root of x plus 5. I have to multiply by the square root of x plus 5 over the square root of x plus 5 because this is 1. And multiplying anything by 1 doesn't change the quantity. Now, the reason I did this is because if we multiply this out, that's x. This is 5 square roots of x. This is negative 5 square roots of x. And this is negative 25. These make 0, and I'm simply left with x minus 25. It gets rid of that square root, which was the challenging part to deal with. So I'm going to quick rewrite this. So I have x minus 25 on the top. Oh wow, isn't this convenient? If I just leave this in its factored form, I have x minus 25 over square root of x plus 5. This makes a 1. So I have 1 on top over the square root of x plus 5. Now I'm going to stick this 25 in there. So I have 1 over the square root of 25 plus 5, which is 1 over 5 plus 5, which is 1/10. Question number 5. All right, so first thing I'm going to do, try to plug that 9 in. 9 minus 9, 0. I can't have 0 in the denominator. So think about the strategies we have. Can I factor it? Well, this right here, this is called a difference of squares. Since this is a perfect square, this is a perfect square, and this is a difference. It's a subtraction. So this factors to x plus 9 times the quantity x minus 9. And we love this because I have an x minus 9 on the denominator now. And this right here makes a 1. So all I need to do right now is plug that 9 in. So 9 plus 9, and 9 plus 9 is 18. So factoring to the rescue again here, just a problem that looked a little bit different. Here's our last example for the day. We have this limit problem. First thing we try is put in that 1 in. 1 minus 1 is 0. So we need to think to ourselves, can this be factored? Well, I can't factor the top. I can't factor the bottom. Is there going to be any 1 that I can multiply this by to make it simpler? No, we can't do that either. If I think about what this looks like, if I graph it, I have a asymptote here, right on the x-axis, and I also have a vertical asymptote at x equals 1. I'm going to draw this rational graph here, so this is what the shape looks like. And a limit exists if from the right side and from the left side I meet at the same spot, and that's not happening here because I have a vertical asymptote. There's nothing I can do algebraically here to manipulate this, so I have a removable discontinuity. So this one is simply a does not exist, and you can abbreviate that DNE because I hit a vertical asymptote. I hope these limit at a point examples helped you today. If so, make sure to like and subscribe.